Data are the raw material of statistics. Gathering good quality data often isn't easy or convenient. But without data, we can't begin to solve the problems and puzzles around us. In this unit, we're going to learn how to make sense of raw data, the columns of numbers that result from practically any kind of investigation. We'll learn that a variable is a quantity that can take a range of values. And we'll see that the pattern of those values is called the distribution of the variable. We'll learn a handy way of picturing distributions called a stem plot. And we'll learn how to extract information from a distribution by looking at its overall pattern and for deviations from that pattern. We've said before that data are the raw material of statistics. Data are numbers, but they're numbers with a context. For instance, 10.3 is a number, but by itself it carries no other information. But if you're told that a baby weighing 10.3 pounds was just born, you know quite a lot. Suddenly, the number 10.3 has a context, a background of information to which it can be compared. If you've had some experience with babies, you know that 8 pounds is about average for a newborn, 5 pounds is a bit low, and 10.3 pounds is quite high. Because the weight of newborns varies over a range of numbers, birth weight is a variable. The world is full of variables. They are anything that can take a range of values, whether it's the calorie count of hot dogs or the scores of students on an exam. The distribution of a variable tells us what values it takes and how often it takes each value. The distribution of test scores on an exam, for instance, might show a range of scores between 63 and 98. Knowing the distribution of a set of data can be extremely useful, a fact the U.S. Army took advantage of several years ago. Basic training. In the past 20 years, the composition of the Army has changed a lot. There are more minorities now, and more women. And because the Army is all volunteer, people tend to stay in longer, making it an older Army as well. These changes have affected size distributions, how big the soldiers are, and how big the equipment designed for them has to be. So for the first time since 1966, the Army is finding out how today's soldiers measure up. 7,600 soldiers were chosen at random to represent the entire Army. Many different variables were measured: foot length, shoulder width, head size, and more than 100 other physical characteristics. The goal was to learn the distribution of each variable, what values they take, and how common each value is. The Army will order more helmets and boots in the most common sizes and fewer for unusually large or small sizes. People with really large or small heads or feet will get something unusual in the Army, custom-fitted equipment. That's cheaper than keeping a stock of very unusual sizes. Let's take a look at just one of the variables measured, head size. We don't have all 7,600 head measurements handy, but here are 30 sizes measured on male soldiers at one base. Suppose we know that the head of one soldier, let's call him George, is 23.9 inches around. Is that a large or small size? It's hard to see where George lies in the unordered mess of numbers. These data are like a library without a card catalog system. The information is there, but it's unavailable. To understand a distribution, it must be organized. And a particularly good way to organize a set of data is with pictures. One way to picture a distribution, such as Army head sizes, is with a graph called a stem plot. Stem plots are most useful when we don't have a large number of individual measurements. To make a stem plot, we first separate each observation into a stem, the first digit or digits, and a leaf, the final digit. In this case, the measurements range from about 20 inches to about 25 inches and are measured to the tenths of an inch. So we'll take the whole inches as stems and the tenths as leaves. First, Arrange the stems in order with a vertical line to their right. Now go through the list of observations, putting the leaf on the proper stem for each. When we're finished, we have this. Now arrange the leaves in order out from the stem. Now we can begin to clearly see the distribution of values. For instance, we can see where George lies relative to the rest of the men measured. His head size of 23.9 inches lies here in the stem plot. It's one of the largest 5 of the 30 soldiers measured. But there's more information to be gleaned from our stem plot. A basic principle of data analysis is to always look first at the overall pattern of a distribution and then for any striking deviations from that pattern. It's helpful to imagine the stem plot turned on its side. The stem plot of Army head sizes now has a single peak at the 22 stem, showing that these values are the most common. Values on either side of this peak are less common. The shape of the distribution is roughly symmetric. That is, the two sides extend out about the same distance from the peak and are roughly mirror images of each other. In this case, the single peak is close to the center of the distribution. Because that's not always the case, it's a good idea to say where the center is by counting up halfway in the distribution. The stem plot makes that easy by arranging the observations in numerical order. We measured 30 soldiers. Half of 30 is 15. Counting up 15 observations in the stem plot, starting at the smallest, lands us on 22.6, so that's roughly the center, or midpoint. A statistician would have a more careful way of saying where the center is, but counting up halfway is a good start. Finally, how spread out is the distribution? Well, the 30 data points range from 20.8 inches to 24.9 inches. The largest and smallest observations give a good start toward describing the spread. In summary, here are the things to look for in any picture of a distribution. The overall pattern, for example, a single peak with symmetry, the location of the center, and the spread of the data. Let's apply our new tool, the stem plot, and our tactics for looking at distributions to another situation.
On the next MASH.
I am sex itself, gentlemen. I am life. I am appetite.
And I'm not taking my clothes off till he leaves.
Hawkeye looks
Reruns of
forward
old
to
comedy series are standard fare on small, independent stations, such as Channel 38 in Boston. Because they can't compete directly with the networks, small stations adopt a strategy called counter-programming, or in the language of television, zigging and zagging.
When the networks are running Cosby and Cheers and all these shows during the week, we may have a hockey game on against it. Altogether different audience. Or a movie, another alternative. And that's basically what we mean by zigging and zagging.
54%.
To zig and zag effectively requires data, information on how many people are watching the shows and what kind of people are watching. That way, Channel 38's programmers can tailor their schedule to capture viewers uninterested in the network shows.
Are those women?
Let's say Channel 38 did a phone survey to determine the typical age of the audience watching a new action-adventure show they were running. 44 of the people surveyed were watching action. Here are their ages in years and months. The computer has changed this to years and tenths of a year. As we've seen, the data aren't very helpful until they're organized with a picture. Let's make a stem plot. We might first attempt, as before, to take the whole numbers as the stems and the tenths as leaves. But that doesn't give a good picture because there aren't enough leaves on each stem to show a pattern. To get a better picture, let's just ignore the tenth digits. Just chop them off. This is called truncating the numbers. Truncating is often a good way to get rid of unnecessary detail in a data set. Now we can make a stem plot with the first digits, the tens place, as the stems, and the second digits, the ones place, as leaves. The tens digit is 0 for numbers less than 10, so our first stem is 0. The first thing that catches our eye about this distribution is a deviation. In this case, the deviation is an outlier, an individual point that falls outside the general pattern. It's not likely that any of the viewers was really 120 years old. It was probably a typing mistake, or perhaps someone played a joke, and the survey taker wrote down the ridiculous age without thinking about it. Outliers like this often point to errors in the data or to other unusual happenings. In this case, since the outlier is probably an error, we can eliminate it. Now we can look at the overall shape of this distribution. There's a single peak on the one stem representing viewers between 10 and 19 years old. The action program clearly draws a younger crowd. That conclusion is reinforced by the overall shape of the distribution. It isn't very symmetric. The two sides are unequal. Not only the peak, but the bulk of the distribution lies on the side representing young viewers. This information is invaluable to the station's programmers. They can now go ahead and schedule action for a time when older viewers are watching other stations. In this unit, we've met some important new statistical ideas. We learned how to display the distribution of a variable with a graph called a stem plot. And we learned to look first at the overall pattern of a distribution, and then look for deviations such as outliers.